Hey guys, hope everybody's doing okay. What we're going to do today is a lesson on drawing Lewis dot structures. So on your note sheet, you guys have a column on the left where you have a bunch of rules, and some of the rules are missing. So what you want to do is look at the screen and copy down the rules first. In this case, 1 through 5 is what we're going to do first. And then we're going to do a couple practice problems in the right-hand column. Take a second and do that, pause the video, write those in, and then instead of me going over the rules right now, I'll go over the rules as we go through the practice problems, and everything should make a little more sense then. Alright, so pause the video, copy these down, and then we'll get started. Okay, the first one we want to draw is a Lewis structure for CH3Br. Now, we draw Lewis structures for covalent substances like this, or molecular substances like this, to show how the valence electrons are being shared between the atoms in the molecule, and how the atoms can obtain an octet, or in this case, hydrogen wants a duet, hydrogen wants 2 valence electrons. And then we'll look at some examples where we want less than 8. There are a couple here or there that are okay with less than 8, and there are some that are okay with more than 8, actually, called an expanded octet. Let's go ahead and start with rule number 1 and see how we progress through these. If you follow this set of rules, you really can't make any mistakes with this. It's pretty straightforward stuff once you get the hang of it. So we have CH3Br. So looking at your periodic table, you find carbon, and ask yourself, how many valence electrons does carbon have? Well, it's in group 14, and all elements in group 14 have 4 valence electrons. We learned that in our previous unit. Hydrogen has 1 valence electron, but there are 3 of them. So we have 1 valence electron times 3 of our hydrogens that are there. And then we have our bromine, which has 7. So if you add them all up, you have 4 valence electrons from carbon, 3 from hydrogen, 1 from each hydrogen, and then 7 from bromine. That gives us 14 total. All right. Every year, students think they're too cool to do the first step, and they think it's really easy, and they skip over it, and they make lots of silly mistakes. So again, if you follow this set of rules, you can't really go wrong here. So add up your electrons, you get 14. And these are 14 valence electrons involved in bonding. Now, there are definitely more than 14 electrons in that structure total, but again, the only electrons we focus on in terms of bonding are the valence electrons. So let's go ahead and see what we could do here to set this up. Step 2 is to draw the skeletal structure, and don't put electrons in yet, and put the least electronegative atom in the center. So hydrogen and bromine have decent electronegativities. Carbon would have the lowest. And you're always going to see here, you'll find some patterns as you do more of these. Carbon is typically a central atom. It's very, very common as a central atom. It makes lots of bonds. So go ahead and do that. And then you want to put all the other atoms around carbon. So let's go ahead and do that. So let's put our 3 hydrogens. You just really put them anywhere. I'll put 1 here on top. Put 1 here on the left. I'll put 1 here on the bottom. And then I'll put my bromine over on the right. So step 3 says draw single bonds connecting each surrounding atom to the central atom. So let's go ahead and do that. Let's single bond all of this. So single bonds are 2 electrons. So 1 dash is a single bond, and that represents 2 electrons. Okay, so there's basically a valence electron on carbon and one of the valence electrons on bromine getting close enough to be shared between those 2 atoms. Okay, so we're going to have 2 electrons per single bond. And now we have to make sure our count adds up here. So we have 2, 4, 6, 8 electrons in the structure so far. Okay, and we have 14 electrons total that we need in our structure. So we're lacking some electrons here. Everything needs to have an octet. That is really a combination of steps 4 and 5 on your note sheet. Step 4 says add in the rest of the valence electron pairs. So hydrogen is very small. Hydrogen has 1 valence electron, and it's okay with only having 2. All right. So in this case, hydrogen has 2 electrons around it because there are 2 electrons in the single bond between hydrogen and carbon. So those 2 electrons are taken care of. Hydrogen is good. Let's not mess with that. Carbon, if you look around carbon, you have 4 single bonds. And remember, a single bond has 2 electrons in it. So you have 8 electrons around carbon. So that's the octet on carbon. That's good. Look at bromine, though. Bromine only has 2 electrons around it with that single bond. It needs to have 8. It needs to have an octet. Everything does except for hydrogen and a couple other elements here and there. So let's go ahead and do that. We have an octet around bromine now, and I put these lone pairs here. So now look at bromine. You have 2 electrons in that bond, 2 on top, 2 on the right, 2 on the bottom. That gives you 8 total. If you add up all of your electrons in this structure, 2, 4, 6, 8, 10, 12, 14. You're finished. Okay? So the first one's pretty easy to go ahead with this one. All right? Step number 5 says if all atoms do not have an octet, then we could swing in an unshared pair and make double or triple bonds. We're going to do that in our next example. So again, start everything with a single bond. All right? Then put your lone pairs around your outside atoms. Work on your outside towards the inside, and you should be fine. And then just make sure you follow the octet rule, and then don't exceed the number of electrons. Okay, so 14 electrons, that's all you need here. Make sure you have 14 in your structure. All right, the next one's a little more complicated. Things escalate quickly here. We're going to look at the carbonate ion. And the carbonate ion from our nomenclature unit is CO3 with a -2 charge on it. Let's go ahead and figure out our total number of electrons. So carbon, we know, has 4. Oxygen, if you look at the periodic table, it's in group 16. Oxygen has 6 valence electrons, and there's 3 oxygens here. And now look, you have a -2 charge. Students are always like, does that matter? Of course it matters. You have a -2 charge. What's that mean? It means this structure has gained 2 electrons. All right, so let's add 2 more electrons to our list, or to our count here. Now, if you have a positive ion like NH4 + 1, then you take 1 electron away, right? So a negative charge is a gain of electrons, and a positive charge is a loss of electrons. We've learned that before. So if you add this up, we have 4 from carbon, 6 times 3 is 18, and then another 2. So total number of electrons here, 18 and 2 is 20, and 4, so that gives you 24. All right, let's go ahead and figure it out. CO3 -2, what's it going to look like? So we have carbon in the middle. All right, it says least electronegative element in the middle, so carbon is definitely it. Oxygen's very high electronegativity. It's the second highest on the table. And put everything else around it. So right now we don't know our shapes yet, so that's okay. We're going to put our 3 oxygens around carbon. And then let's go ahead and connect them with single bonds, because step number 3 on our list says draw single bonds connecting each surrounding atom to the central atom. Single bond, single bond, single bond. Okay, step number 4, add in the rest of the valence electron pairs. So we got to be really careful here. We have 2, 4, 6 electrons in this structure so far. Let's go ahead and work our way through this to get 24 total electrons in our structure. So we have 6 so far, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so there we go. It looks like we're done. And the key word there is looks. It looks like we're done. We're not. So let's go ahead and double check everything. So let's follow our basic rules here. Do we have the correct number of electrons? Absolutely. We have 24 electrons in the structure. We need 24 electrons total, according to our count. The next question we have to ask ourselves is, does everything that wants an octet have an octet? So let's go ahead and look at that. Does oxygen have an octet? Well, of course it does. We have 2 electrons in that bond, and then 6 electrons with those 3 lone pairs. So you have 2, 4, 6, 8. All 3 electrons we drew the same way. All 3 oxygens we drew the same way. So this oxygen up top has 8 valence electrons, oxygen on the left has 8, and the bottom has 8. So they look good. Let's double check carbon. Carbon has 2, 4, 6. Okay, wrong. Right? So we can't have only 6 valence electrons. Carbon needs to have 8. So here's what students do all the time. It's very frustrating. So they know 24 electrons total. That's what you need to have in your structure. And they go ahead and they just write carbon in the middle, put their oxygens around it, they put all their lone pairs, and they do this. Like, okay, great, carbon has an octet. I'm done. But if you look at this, you have 8 electrons around each oxygen, and then another 2 electrons over here. Count them up. Now you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. You have 26 electrons in this structure. That can't happen, right? So this is wrong. We can't do that. So let's get rid of that lone pair. We can't just get 2 more valence electrons out of no man's land. It doesn't work that way. So step 5 on your note sheet says if all atoms do not have an octet, which is what we have here, then swing an unshared pair from a surrounding atom to connect to the central atom to form a double or a triple bond. So let's go ahead and do that. We really have multiple options here of what we can pick from. But let's just pick a lone pair anywhere. Let's pick this lone pair right here on oxygen. Now, this lone pair is only counting as 2 valence electrons for this oxygen atom. All right? It doesn't count for carbon. So how can I get this lone pair of electrons right here to count not only for this oxygen, but also for this carbon? What we can do is take it and move it here and make something called a double bond. All right? So we said earlier on the last slide, a single bond is 2 electrons. A double bond would be 2 dashes, and that's 4 electrons. Let's go ahead and I'm going to clean this up and do that. So I'm going to move this lone pair over here. I really could have picked any lone pair on any oxygen to do this. So I'm going to erase it from here. And I'm going to move it here. There we go. Now I have my double bond. Let's double check everything. Let's count our electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Perfect. I need 24. Oxygen up top has an octet. We're good to go. Oxygen on the left, octet. Good to go. Carbon in the middle, 2, 4, 6, 8. Good to go. And the oxygen on the bottom, 2, 4, 6, 8. Good to go. So everything has 8 valence electrons here. Everything has an octet. Everything looks perfect. So now we are done with that example. All right, so once I teach this, students start to go double and triple bond crazy. So don't do that. Start with the basics. Connect everything with a single bond first. Okay? Then fill in your valence electrons. See if your electrons match the number that you need. And then you can go ahead and fix things from there if something doesn't have an octet and you can't add more electrons. Now, I could have picked any oxygen to do this with. So you could actually draw something called resonance structures here. Resonance structures are basically just similar versions of this. I just pick a different bond to make my double bond. So I could also have this. I have my double bond up top. And I put that arrow in the way here. That's unfortunate. Okay, so that's 2 resonance structures for the carbonate ion. And then let's do one more. I could have my single bond up here. This is getting a little sloppy, I'm sorry. We put our double bond over here. And still have our single bond down here. Okay. One other quick note here. What you should do is, this is an ion. So you should do something like this and put it in brackets. Put -2. Because if some other person's looking at this, they look at this structure, they're like, oh my goodness, I have CO3. Well, CO3 should only have 22 electrons in it. Well, no, this is CO3 with a -2 charge. Oh, okay, of course that makes sense. We need 24 electrons now. Do the same thing over here. Okay, ions go in brackets with the charge. That's important. All right, takes care of that. So you're going to do a couple practice problems in a minute. Let's go ahead and do one other exception here. Let's look at an exception, I should say. Rules 6 and 7 on your note sheet. You can have different exceptions to the octet rule. So these are important for honors chem to understand. Group 13 elements are okay with only 6 electrons. So boron, aluminum, gallium. You don't really see gallium too often. You mostly see boron and aluminum. So they're okay with 6 electrons. Now they're okay with 8 as well. So don't think boron can't have an octet. It definitely could, but it's okay with 6. And then step 7, if everything has an octet, but more electrons still need to be placed, you can put them on the central atom. These are called expanded octets. Only honors and AP students are responsible for these. Central atom can have an expanded octet if the element is in the 3rd period, so 3rd row of the periodic table or higher. So elements with d orbitals can have expanded octets. Your d orbital, remember, it doesn't start until level 3. The first d orbital you have is 3d whatever, right? So because of that d block and those d orbitals, it helps make an exception to the octet rule. You could fit more electrons around that central atom due to that D block that's present there. So again, this only goes for the central atom. You can place extra electron pairs around the central atom, and this is very important, up to 6 pairs max. There are actually some crazy shapes with 7, maybe 8 pairs. We're definitely not responsible for those. I can't even think of the names of those off the top of my head. They're pretty neat, but we're not responsible for those in Honors Chem. Okay, let's take a look at an example of this, and then you guys will work on a couple. So your third period starts here with sodium. So anything from the third period to the end of the periodic table, any of these elements technically can have an expanded octet. All right, let's look at SF4. So SF4, sulfur is in group 16. That has 6 valence electrons. And fluorine is in group 17, which has 7. And you have 4 fluorines. Okay, so 7 times 4 is 28 electrons, plus another 6. That gives you 34 electrons in this structure. So it only makes sense to put sulfur in the middle, and then the fluorines around it. So I'm still following my old rules as of now. So put my 4 fluorines around it. And then my rules state single bonds for everything, right? And now I go ahead and figure out my octets. So step 4 on your rules, it says add in the rest of the valence electron pairs. So right now I have 8 electrons in this structure. And then let's go ahead and start up here. So it's 10 electrons, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So again, a very common mistake here is students don't pay attention to this, or they don't do it. It's very frustrating. And then they go ahead and they draw this structure. And they're like, I'm done. And it looks perfect. It looks fantastic because sulfur has an octet. Each fluorine has an octet. You're like, why would I need to do anything else here? But like I went back to the beginning of the lesson here, I said students think they're too cool to do that first step, and they make dumb mistakes and they get points taken off. Prime example of that's right here. So count up your electrons, you have 34 of them, and then check your structure. My structure only has 32. I have 8 right here, I have 8 right here, 8 here, and 8 here. All right, 8 times 4 is 32. I need 2 more electrons. Well, what the heck? Everything has an octet. What do I do here? Go back here to this slide. It says if everything has an octet, pardon the horrible grammar, if everything has an octet here, but more electrons are needed, that's the case we're in, the central atom can have an expanded octet if it's in the third period and higher. Higher means like period 3, period 4, period 5. It doesn't mean higher on the periodic table. It means a period higher than 3. So let's go ahead and find sulfur. Sulfur is right here. It's definitely in period 3. Here's period 1, 2, 3. So we can have an expanded octet. So you could store an extra lone pair on sulfur. That's actually going to give us a pretty neat shape when we learn about those. All right, so that is SF4, and that's really the lesson for today. So what you guys are going to do is go to the next page in your packet, and there's some like in-class practice. So it's only it's only 5 problems. One of them I give you the structure and how to set it up. Some of the other ones are very easy. Little intro to this. So none of them are all that rigorous on that next page in your packet. Then when we get in class, we'll actually do some in-class practice problems and warm-ups and get some help on this. But you should be in pretty good shape if you follow these rules and you pay attention to this intro video. We're just going to expand on this. This is the foundation of what we're doing for the rest of the unit. So everything starts here, then we build on it. We determine what shape this is. We talk about something called hybridization, different types of bonding that occurs here, and then ultimately polarity. So if you get this wrong, then literally every single other thing is incorrect. So please make sure you pay attention to this lesson. Go back and watch it over if you need to, or different parts of it, and really try to do that practice and pay attention to the practice. So we do well for the rest of the unit here with this as the foundational skill we need to know. All right, guys. So ignore that. Just go to the next page and work on those. I do have a review video for that posted for you, and I'll link that either here or on the roadmap for you guys to check those over. All right. Thanks, guys.